All right, so when we first introduced the idea of a derivative way back in chapter 2, one of the first things we did at the beginning of chapter 3, immediately after, was to make a list of all the properties that we would frequently use that derivatives satisfied. So we're going to do something similar now. We're going to just state a few properties that are satisfied by this antiderivative structure. So here they are. So I'm going to state some properties. One of the things that will be handy, the first one, well actually, and I'll start this by saying let k be some constant. Okay, and here's the first property. If you take a function f and you multiply it by the scalar k, the result is another function. And you can ask the question, what is the antiderivative of that function with respect to x? And that's a reasonable question. It turns out that you can calculate that by taking the antiderivative of just f of x on its own without considering that constant multiple or constant multiplier k. And then once you're done finding the antiderivative of f, you can multiply by the k afterwards. And that's what the first property says. It says you can do that. So essentially, just like with derivatives, you can pull constants right out of antiderivatives. And you can pull it out of this general indefinite integral. Okay, so that's the first property. The second property is another property that also holds for derivatives. And it works as in the following way. If I take two functions, f and g, and I add them together, and then take the general antiderivative of the result, that's what I've written here, right? This says add f and g first, then take the antiderivative afterwards. Well, another thing you could do is you could consider the function f separately, take its antiderivative, and then take the function g of x and take its antiderivative, and then add them together afterwards. And that's what the second property says. It says that those two things are equal. So I can safely put an equal sign in between them by the second property. That's what this property tells you. And then property 3 just says you have a similar one for subtraction. If I have f of x minus g of x, and I want to find the antiderivative of the result with respect to x, if I want, sometimes it'll be easier to do so. I can take the antiderivative of f of x, and I can take the antiderivative of g of x, and then subtract afterwards. So really it just gives you a way to turn more difficult antiderivatives into simpler ones. This focus might be going out a little bit again. I'm just going to adjust it. Oh, maybe that's about as good as it's going to get. Okay, let's look at a couple of examples. And these ones will be a little bit more... Oh, actually, I'm getting a little bit ahead of myself. Well, I can finish writing the word examples. And actually, well, how about I write them down now? Yeah, no, well, come back to that. Let's write this rule that we're going to use for these examples. Not power rule. So that's almost everyone's favorite rule for derivatives is the power rule. Then there's one for antiderivatives as well. So we're going to write it down. You have to be a little bit careful, but it's quite nice and straightforward to work with, just like the power rule for derivatives. But there's a technicality you have to watch out for. So here's the general rule that tells you how to find the antiderivative of a power function, x to the n. So, and it might be helpful to see why this works. It may be helpful to look back at our previous page and try to watch and see a pattern. Like if I have x cubed and I take the antiderivative, pardon me, if you take the antiderivative of x cubed, what happened? We got x to the 4 divided by 4. So the exponent went up by 1, and then whatever that new exponent was, we also put it as a denominator as well. And you notice that also worked here. When we had x squared, when we took the antiderivative, the exponent went up to a 3, and then we just divided by 3 after. That's actually pretty illuminating as to what's going to happen in general. If I want the antiderivative of x to the n, well, let's try x to the n plus 1. but then I'll divide by n plus 1 after. And that seems like it ought to work. And you can check. I'll just work it out down here. Derivative with respect to x of x to the n plus 1 over n plus 1. What happens? Well, I'd get 1 over n plus 1. I can just pull that constant out first and then differentiate the x to the n plus 1. And I would get n plus 1 x to the n plus 1. N plus 1 x to the n, pardon me. Then the n plus 1s would cancel, and I would just be left with x to the n, which is exactly what you're looking for. You want to get x to the n back. So this really is, it looks like this actually works. This is the antiderivative of x to the n. But there's one case when that's not going to work. And this is another case where I'm going to suggest that you pause it for a few seconds. Pause the video for a few seconds and see if you can spot the issue. When would this not work for an antiderivative of x to the n? Okay, maybe you've caught it, maybe you paused it, maybe you didn't, but in any event, notice that this is not going to work when n is equal to -1, because then your denominator would be 0. So this actually only works if n is not equal to -1. So you have to add that stipulation in. Well, what if it is equal to -1? Does that mean you can't do anything? Oh, that's not true either. Actually, if it is equal to -1, you could still do something, and I'm just going to pull back the previous page here. Or maybe not quite yet, if n is equal to -1, then x to the n is actually just x to the -1, which is 1 over x. That's this one here. The antiderivative of 1 over x is the natural log of x. So that's why we'll just use the natural log of x. And actually, I'm being a bit sloppy here. I should say plus c, and I'm going to do the same thing here. I should say plus c, because we need the constant of integration in either case. So I don't have very much room to squeeze that in here, but there should be a plus c after this whole fraction. So I'm just going to put it there. Unfortunately, that looks like it's almost attached to the exponent. But that's your power rule. And it's natural log of x plus c if n is equal to -1. Okay, and this is just bothering me. I can't stand it, so I'm just going to write this out one more time, because that plus c is just in an awful place. So in case anyone's confused by that, let me write it out carefully one more time. So the antiderivative of x to the n, it's going to be x to the n plus 1 over n plus 1 plus your constant of integration. This is if n is not equal to -1, and it's going to be the natural log of x plus your constant of integration if n is equal to -1. So that's what I meant to write, so pardon me, ignore that. I don't want that plus c to get confused as being added onto the exponent. So that is your power rule. This is the rule you're going to use most often when you're calculating antiderivatives, which that's what we'll do in the next few examples. Okay, so I'm already at 8 minutes here, so I'm going to stop the video and start another one.